So let's talk about energy and simple harmonic motion. I made a video because the reading, I don't think, I didn't see any graphs, and that's an important thing to look at. Some of the algebraic expressions and stuff we can get pretty quickly. But first, let's look at the mass on a spring. And so we're going to put this thing into simple harmonic motion by displacing it. Let's say we pull it out. So we're going to pull it out, here. And then we're going to let it go. So this thing's going to oscillate back and forth between positive A and negative A, where A is the amplitude. So at time 0, I'm going to get a position graph going here, and then we'll talk about the energy. So we're going to start at a positive A, and then it's going to move back towards 0 to negative A, and then turn around and come back. And so we know that we get this cosine function that kind of does this kind of shape. Kind of freehanding these. So keep in mind that what we're looking at is we're looking at one period. So it's about to repeat its motion here. So that would be big T. Now now we can talk about energy. So when we stretch the spring out, we've learned previously that that's called spring potential energy. And so we know that there's going to be some maximum spring potential energy at the same time. So notice this is over time, so I'm lining up the times. We're going to come back and do this with position. But when this thing is at maximum amplitude, then we're going to have all spring potential. And then as it moves towards equilibrium, well, at equilibrium, the spring is neither stretched nor compressed, so we end up getting 0 energy there. And then it goes to the other side, compresses the spring, and so we get a maximum on the other side. So what you end up seeing is you get kind of the same graph. So we would end up like this. You know what? I shouldn't. Kind of messed up this graph. This should be, let me redo that. Because our spring potential is 1/2 kx squared, so we're not going to end up with a negative. So it would come down and then bounce back up and reach a maximum, and then come back to 0, and then back to a maximum. And so this would be our potential, our spring potential energy. However, there's another type of energy. So this energy, when we release this thing's going to get faster and faster and faster until it's here at equilibrium. And that's kinetic energy. So it starts with 0 kinetic energy, and then what's going to happen is all this energy is being shifted over into kinetic energy. So you get a graph like this. So you see I get a maximum where this one's a minimum. And it does this kind of thing. I didn't draw it very well, but hopefully you get the idea. So at amplitude, we have gravitational potential is a max, and the kinetic energy is 0. At equilibrium, the potential is 0, and the kinetic energy is a max. And then likewise over on the negative side, potential is max, and kinetic energy is 0. So these just oscillate back and forth. The energies oscillate back and forth from one to the other, such that there's a total energy in the system. And that total energy is going to be right here. So we could draw it along here, and that would be energy total. So at any point in time, if I add up the two energies, it should add up to be that. Now I didn't draw my pictures very good, but there's some total. That's the idea. This is fixed. There's no friction. There's no work being done. Okay, so what if we wanted to know the actual energy? Or you know what, let's look at this graph. This graph of displacement. So this is energy versus displacement. So equilibrium is at the origin. And then we have to define some maximum amplitude. We'll do a positive amplitude over here and negative amplitude over here. So this gives us it's a little cleaner picture of what's happening with energy. So for spring potential, I'm going to have a maximum at my two amplitudes. Now, this is potential in terms of position. So this graph is a little different. This one was in terms of time. But what I'll see is that it kind of does this thing. So I get a quadratic. And we'll come back to this. So that's my spring potential. And then my kinetic energy, again, at amplitude, it's at 0. And then it kind of curves and does this thing. So we get a maximum at equilibrium, and then it comes back to 0. So this is kinetic energy. And again, we have some total energy, which is going to be the upper boundary of this. So it can never pass this. This would be E total. I'll come back. I'll talk about gravity wells, but okay, so to show that that's quadratic, or if we wanted to know the kinetic energy at equilibrium, well, all of your spring potential at equilibrium, so let me write at equilibrium. Equilibrium. Then the spring potential is going to become, all of it's going to go over to kinetic energy. So it's equal to the kinetic energy of the mass. And then the spring potential energy is 1/2 k x squared. And that's displacement from maximum. And on the other side, kinetic energy is 1/2 m v squared. So you can see why they're both quadratic. This one's flipped over because it's an increasing. Anyway, let's finish the math. So if we want to know the velocity, the halves are gone. We divide by m. So you get k over m times x squared equals v squared. And then we'll take the square root of everything. So over here you get the square root of k over m times x. It's the square root of a square, so it comes out. And that would be your max velocity. So you can see the maximum velocity depends on the k value and the mass, and then your x. X would be actually your displacement. So this would be amplitude. So if you want a general equation, it's going to be the velocity v max. That's not v max, that's v in terms of x. Would be a root k over m. Your book, I think they do a slightly different derivation. I didn't go through it all, but this is basically the idea. Okay, let's look at how about a pendulum? So pendulum, same concept. We have a mass hanging from a string or something, and then we're going to release it. And so we define equilibrium. This would be 0. And it's going to swing across, and so we get some max amplitude. In this case, it's going to be the same type of thing. Let's look at energy. So we'll just do energy. And the position. I'm going to go ahead and just do angular position. So the angle that's being carved out here. So the maximum would be here, so that would be my amplitude, my negative amplitude, and then I'd go to some positive amplitude on the other side. And what we're getting here is when we raise this thing up and hold it here, that's gravitational potential energy. And then we release it, and it's going to come down and get to a max speed here, max kinetic energy, and then go back into gravitational potential. And so this, the graph in general, you're going to end up with some gravitational potential up here, and then it goes to 0, and then it comes back up to a maximum, UG. Now keep in mind UG is mgh. However, this is in terms of angle, so we have to change h. In order to get h, what we would look at is this distance here. I'm not going to get into the math, you don't need to know it. Just know that it kind of does the same thing. And then kinetic likewise would look like that, inverted. Whatever, goes to a max, you get the idea. So it's this interchange between each other. I did want to talk about energy in general though. So for an oscillator like this, we have a couple different types of graphs for energy. One is going to be like that. Well, here, I'll just keep it like this. Let's just do this here. Okay, so this is potential energy over some distance, x. And so depending on where our total energy in the system is, will define what happens to the object. Like, let's say I'm right here. That's my total energy. Then this object is stuck. It can never get out of this. We call it a well. So this is a potential well. So the object is in motion and it's like rocking back and forth, but it will never get enough kinetic energy to escape and get out. So this could be gravity or the spring potential or whatever it may be, but it's stuck there. Whereas if I lifted it and I put the total energy up here, then you can see that this object will escape on the other side. So if I have it up here, when it comes to this side, that's going to be all transferred over to kinetic and it's going to have enough energy to get out. And so it's kind of like a cap. Your total energy will put a cap on it. And these types of wells come up in all sorts of different aspects. Gravity, a gravitational well, kind of looks like this. Really steep. So you got to think of like the Earth is down here inside of the well. And so to get out of the well, it takes a tremendous amount of energy that we have to put into the system to get this thing to pass out and finally escape gravity. So rockets, we spend most of the energy just lifting it up off the Earth. And the reason is we have to get up above this well, climb the wall, and then you're out, then you're free. I think that's about it as far as energy. Just know that there's a total and the interplay between the two. It's all kind of qualitative stuff. You will have some calculations, but just remember conservation of energy. So you're moving from one form to the other.